Hi everyone, today we're going to be finding the potential energy of a planet in orbit. So let's start off with the planet, which has a center that we'll call R1. There's another object that is a certain distance away from it at point R2. And we know that for the object to get from R1 to R2, the work done must equal the change in potential energy from these points. So basically, the work done is equal to the potential energy at R2 minus the potential energy at R1. We also know that work is equal to the integral from R1 to R2 of the force vector with regards to the displacement, which we'll call R. And we know that the only force acting on the object at both of these points is mg or Fg. And we know that Fg is equal to the gravitational constant times both of the masses divided by r squared. So now that we have our force vector, we can continue to simplify the integral, which is pretty simple. And this will be equal to, let me just continue solving first, will be equal to times 1 over R1 minus 1 over R2. And as we found earlier, the work done is equal to the change in potential energy. So let's equate that. So when the planet is in orbit, we basically want R2 to be at a point where there is no potential energy because there is no gravity anymore. So how can that happen? When we take the limit of both sides as R2 tends to infinity. And so we see here that the potential energy at R2 is 0 because there's no gravity, so that's gone. And then 1 over infinity tends to 0, so R2 is gone. So now we have the equation. Sorry, this is supposed to be an R1. So now we have negative u of R1 is equal to GMM times divided by R1. So the potential energy of the planet in orbit is the gravitational constant times both masses divided by r. That's it.